Here in Online Lecture 2, Part 1, we're going to talk about data classification. When we collect our raw data, we want to see patterns. We tend to want to group things together that are similar and separate them from the things that are dissimilar. The classification of how we group things together so we can display it on a map, it's very important. For example, we do COVID testing for all 92 counties of Indiana. How do we group the results? Naturally, counties with high number of cases would be grouped together, and those with low number of cases would be grouped together. But of course, it's not as simple as that. In fact, there are several different ways in which we can group or classify a particular data set. And so here we've got 4 of them that we can find in ArcGIS: equal intervals, quantiles, mean, standard deviation, and natural breaks. The book goes in and talks about a few different ones, and there's several more out there. Before you do any classification, it's important to ponder these particular questions that we see here. And as always, we need to think spatially. How is it distributed? Is it normally distributed? Is it clustered? Is it dispersed? Is it random? Can you explain the data? How did you get the data? What are you trying to do? Once you have the data, you need to know how it is distributed so you can then explain it, show it, visualize it on a map. And then you determine how many classes should you use. And how do you compute that? As you'll see, the legend needs to make sense as well. The legend's important because that's where the classifications are defined and or described on the map. Although it might seem quite obvious, whatever you're visualizing or classifying is at one particular point in time. So what we'll do is we'll work with the particular data set for this particular video. In this data set, it's one moment in time, 2030, and it's a population projection. So it's a projection out in the future. From stats.indiana.edu. It's a labor projection. And so what it is saying is it says, okay, for every single county of Indiana, we're going to give a particular value, the percentage of the population for each county in 2030 that we expect to be working and over the age of 65. So what are our expectations? And so what we can go ahead and we can kind of theorize, okay, well, where are the younger counties of Indiana? Well, those are going to be our college towns. And so places like Monroe County, places like Delaware County, where Muncie is, Monroe County, where Bloomington is, Tippecanoe County, where West Lafayette is, and Purdue, those are probably going to be places where you're not going to see as large percentage of the population over the age of 65 that are be working in the year 2030. Further, not going to be in our urban communities. Our urban communities typically are younger, so Marion County. We should not expect to see a large population of over 65-year-olds in the workforce projected for the year 2030. So what's our purpose? And so what I'm trying to do is I'm trying to identify, in this case, we want to see those 4 or 5 counties that really are at the top in terms of having a large percentage of the population over the age of 65 in the workforce in the year 2030. And so here I have a few more questions listed in terms of things that kind of to consider as you work through your data. And not everything can be mapped. And so it's very important to make sure you're not wasting time. Make sure that you're doing what you're expecting to do. One of the questions often asked is how many classes should we use? Well, experts say between 4 and 7, so we're going to use 5 as the default for this particular video in this particular example. So here's our data set just to give you an idea of what it looks like. It's got its GeoID. The 18 is the state of Indiana, and then these smaller numbers are the counties. And so county number 3, county number 5, county number 7, and so on. So this is the unique identifier that places it, that has that location specific information. And then over here, of course, is our values. And so this is the percentage of the population for this county, 6.9%. Of the workforce will be over the age of 65 in the year 2030. So you can see how you have different counties with higher values. 13 has a 12.10. And so naturally, we want to group those higher numbers together and separate them from the lower numbers. So there's a few different ways to do that. Let's go ahead and start with the first one called equal interval. This here is the easiest way. Let's say you want 5 classes. How do you define the range of each class? Here's the formula. So you essentially get the high value by the lowest value, and then the number of classes you want, you essentially divide that result by 5. So for example, our high value is 10, our low value is 2. 10 minus 2 is 8. Then divide by number of classes, 8 divided by 5. And then that's how we essentially start to then develop the upper and lower limits of each class. There are some pros and cons of this one. Like I said, it's very easy to calculate. That's why it's often used. And this was often used before. We had a lot of the mapping software that's now quite powerful, and we can do a lot of different things with. So when I learned cartography, equal interval was my preferred one because it was easy. It was simple to do. The results are fairly easy to interpret. And the legend, one of the things, it does not contain any missing values. I got an example of this. The book shows an example of a different classification scheme in which it does create these gaps in the legend. I'll show you what I mean here in a minute. One of the major disadvantages is it doesn't consider the underlying data distribution. So you can get an unequal count in each class. So let's go ahead and take a look at the map. All right, so this is a map, and so this is in ArcGIS, and so I took that data set and I chose the equal interval. So you see equal interval is my choice here. I have my 5 classes. I'm going to use the same color scheme for all these particular maps. And so let's go ahead and take a closer look at this. So the legend, there's no gaps in the legend. Essentially what I mean by that is we see from one number to the next, 0.96, 0.9, there's no gaps. And so another example I'll show of where there are gaps in the legend, and that can be confusing to the map viewer. Key to this one here is right here. So the equal interval, notice how the spacing here is the same. And so this is the data distribution. This is all of our data. This here is the mean. So you can see there's some outliers here. Not really, it's pretty normally distributed other than the outliers. So we have this particular spacing that's all the same. And so when we think of this one, we think of it being evenly spaced, but unevenly filled. What I mean by that is these particular categories contain different amounts of observations. So just a few in there in this dark blue, just a few in this one, a ton here in this green. So this green here. And so it's unequal number or unequal filled in terms of these categories, these 5 separations, but they're evenly spaced. And you'll really see this when I compare it to the next one, quantiles. And so I zoom into the map and we can see particular counties really stand out here. This here is Brown County. Brown County is going to be our recreational county. This is the one county of Indiana that right now is a retirement destination. So that makes sense because you have a lot of retirees, that you're going to have a lot more people working in the workforce who are older, people who might have a job, a part-time job working at a museum, working at an art studio or art gallery, or maybe a furniture store in Brown County. Other things you got going on is you kind of have this area down here, and then also up here. And so I'm going to attribute this to some agricultural areas. And so there's not much agricultural areas of southern Indiana, but in these particular counties there is some. There's also some coal mining happening. I don't know really, that doesn't really mean anything for old people. We're not going to see an old workforce because of that. This is farming area, so perhaps that's what's going on, but we really can't see kind of the data really isn't really showing us beyond these top 4. We can kind of see some other areas, but maybe this isn't the best for this particular objective. So we'll take a look at another option. So next up is the quantiles. And so what this is, it kind of takes the data and then ranks it from its smallest value to its largest value. And so it ranks them along the number line. Here we have an equal number of observations placed in each class. So where previously I said that whole evenly spaced but unevenly filled, here we have the inverse of that. We have the unevenly spaced but evenly filled categories here. So observations in a class is obtained by the total number of observations and dividing it by the number of classes. So another one where it's relatively easy to calculate. Now, when we think about limiting the legends and the different groupings, the minimum and maximum of the class is a nice way to kind of separate them. Also, you can use the average of the upper limit of this class and the lower limit of the next class to kind of use that as the separation or the divide between one classification grouping and another. And like I said, the description is rather easy. I mean, we know 2 classes, it's going to be 50% of the observations are going to be found in those 2 classes. If we have 3 classes, 33.3% are going to be observed in each class. If we have 4, 25%, and so on. So we think about those classifications. Every single one is going to have the same number of observations within that class. And so now we see this particular map here. We've got over here, we've chosen Quantile. Once again, same color scheme, 5 classes. And now we start to see a little bit more of that particular pattern here. So Quantile, in this case, is good for not really showing those top ones, like those top 2 or 3, but for breaking it down and showing kind of those percentage groupings. So now we can see dark blue is going to be representing about 20% of the data. And then the royal blue, another 20%. And then our teal, the middle 20%. And then we have our light greens and what is that, pale yellows are going to be in the bottom 20%. And so we can see essentially how this quantile shows a different pattern on the map, but it's the same data. So it's the same data. So essentially we have the same data in which it's now producing a little bit different patterns that we can then learn from. Go ahead and take a closer look at this particular legend. In this case, we don't have any gaps, but this one is prone, the quantile is prone to having these gaps in the legend. All right, so here we see this particular spacing is not the same. And so beforehand, the spacing for the equal interval was the same. This time it's not. This time it's all about making sure that each of these has the same number of observations within each of these classifications. Comparing the equal interval to quantile, once again I said the equal interval is really good at showcasing those extremes. In this case, those 4 or 5 counties that really have a high projected population of old people in the workforce. Whereas the quantile, then yeah, you can start to see, okay, some rural Indiana for sure. So we have urban Indiana, and then we have rural Indiana considerably, where we have an older population, and so that makes sense why the workforce, thus in 23, is going to have a larger percentage of older people over the age of 65 working. So some pros and cons, like equal interval, it does not consider the data distribution. So it's one of the things is you can, it doesn't really take into account as far as the distribution of the data, which essentially uses this formulaic method in terms of, okay, we have 5 classes, all of them are going to have the same number of observations. So that's just, so it doesn't really consider as far as the data distribution like the next 2 do. You can have gaps in the legend. This is from the example. So when I talk about gaps in the legend with quantiles, this is what I mean. So you can have these classes in which you'll have these gaps. And so right here, 2.8 to 3.1, there's a gap. 4.9 to 5.2, a gap. 6.3 to, so this is something to keep in mind with the quantile, is that if you're looking at a map, and it might be confusing, especially there in the legend, if it has those gaps. Well, that's kind of a common problem or common challenge with the quantile. So another alternative to creating a class boundary is essentially the average of the highest value in a class and the lowest value in the next class. And so just compute an average, and that essentially creates a line or a boundary for each class. So that's just another alternative way to do this. So I can use this particular to kind of compare and really see here how the equal interval has this evenly spaced but unevenly filled groupings, whereas the quantile is unevenly spaced but equally filled. And so each of these colors has the same number of observations. So hopefully that helps to flesh out the differences between these 2 classifications. Next up is the mean standard deviation. This one assumes that the data is normally distributed. And so I'm not going to go too much into that, but just if that's something that you want to do, and you need to keep this in mind, that you need to standardize your data. And so if your data cannot be standardized, then you can't do this particular method. So this assumes your data is normally distributed. The class ranges are calculated based on the mean and standard deviation. So we can see here, class 1 is from the mean to 2 standard deviations. And so then we see the next class, mean to 2 standard deviations to the mean and 1 standard deviation. And so essentially what we're doing is we're using the mean and the calculated standard deviations to then create the groupings. And so let's go ahead and take a look at this. And so once again, we have our normally distributed data. And so here we have the mean, and then we have one standard deviation this way, one standard deviation this way. And so once again, this represents 68% of the data. And we combine, add in the next two, that represents 95% of the data, and so on. So this then is the reason why I last time started to talk about the mean and standard deviation, is now it's going to be more understandable when we look at this particular mean standard deviation classification system. And so here, the particular pattern here, we can see it's pretty good. We got one standard deviation as our interval size. And so essentially what this is good for is we know, because the means right here in this teal kind of area, we know that the blues are going to be observations or counties that are above the mean, and the yellows are going to be observations below the mean. And of course, the teal or that green, whatever that is, where my cursor is right now, that middle particular color is going to be right there near or around the mean. And so here the groupings, you can see how they're done, from half of a standard deviation to a half of a standard deviation, from a half to 1.5, 1.5 to 2.5 standard deviations, and then those blue, dark blue, are greater than 2.5 standard deviations away from the mean. So those are going to be our outliers for sure, but those outliers on the right tail of our distribution. Here they're actually evenly spaced, sorta, but once again unevenly filled. And so we can see the spacing is actually evenly spaced here. With the idea where we're from one half one way to half the other way, from negative 0.5 to negative 1.15, and so forth. And so the spacing is essentially even, but as you can see here, the categories are unevenly filled. So here you'll see the distribution is pretty similar to the equal interval. And so once again, we have the same situation where both of these are evenly spaced, and then the distributions are also unevenly filling each of these categories. And so this is pretty similar in terms of what we're going to see here. So these are probably going to produce pretty similar outcomes when we look at the maps. And what I also did is I went ahead and I said, okay, this particular pattern in Indiana of where old people over the age of 65 in 2030, the percentage workforce, that whole thing, I said, well, I'm going to do a spatial correlation to see if this is a pattern that's random, dispersed, clustered, and it is clearly very random pattern. So there isn't really a clustering happening here of old people, let's say, in Indiana counties. It's a very scattered particular pattern. All right, and so what I have here is the quantile next to the mean standard deviation. And so you can see how the quantile, once again, breaks those groupings. So you can see those groupings down. So those top groupings are going to be a little bit larger. So it's going to have higher numbers of counts, higher numbers of observations in those dark blue counties in blue, whereas here, this is going to, very similar to the equal interval, where it's really showcasing and really pointing out those particular counties that stand out on the sides or on the tails of our normal distribution. So those outliers, those counties that really stand out as far as having a high percentage of the workforce, and those that stand out as far as having a low percentage of the workforce. So Marion County, Johnson County, Tippecanoe, Delaware County. Oh, those are those counties. Scott County down in southern Indiana. I don't know why that's so young. Anyway, so these are going to be our younger percentage workforce counties. And this makes sense because we have younger people there. The overall population is younger. What is natural breaks? And so this is one in which the book kind of talks about. And keep in mind the book's a little dated, but this is the one in which it's also known as optimal, and we're going to use the Jenks particular algorithm. And it's a very simple idea. The whole idea is it tries to find the natural breaks in the data. And all it does is try to minimize the difference between data values in the same class, but at the same time maximize the difference between classes. So here we have our map. We have our 5 classes using the natural breaks Jenks in our same particular color scheme. So we see our groupings over here, our legend. So let's go ahead and take a closer look at this. And so here we have our spaces. And so here, the natural breaks is just looking at the data. And so it says, okay, naturally, where would I put this? Well, let's put this right here because we've got these outliers here and we want to distinguish there. Here we have another grouping. And so this is just kind of intuitively looking at your data, and it does it for you. That's what's nice. And it tries to find the natural breaks in the data based on this kind of this whole idea, this fundamental idea that we're trying to minimize the differences between the same class, trying to minimize the difference between the class, but we want to maximize the differences between the groupings, between the colors. So here's the mean standard deviation. So we kind of compare that to natural breaks, and where I like the natural breaks here is, once again, we see those 4 counties that really stand out, but we can also see now those other counties that are also high, also above the mean, but they definitely are more recognizable here in the natural breaks. So which is the best classification to use? Well, that's where you kind of, once again, you kind of figure it out yourself. You kind of compare, you guess and check, you make a map and say, you know what, I don't like that one, let's try a different one. What's nice is figure 4.5 in the textbook is a good job of showing that, and I think I have that right here. So this is that figure 4.5, and so it does it good as, okay, we have all these various things, and so, ease of computation, all of them are very good, it looks like. So assist in selecting number of classes. The optimal is the one we just did, and so natural breaks optimal. Now, for the most part, it's been combined, let's say. And so here is a good chart to kind of look at as far as the pros and cons in a nice, simple, easy visual way. All right, so here are all the 4 maps that I just created. Which one's the best? And so that's just kind of up to you, the creator, the cartographer, to come up with whatever one you think is the best. And once again, whatever this is best for your objective, whatever is best for your audience.